Now, in the previous sections, we talked about multivariate analysis where you solve the three variable case. So we looked at a number of different data sets. Each of them were like three variables. We looked, for example, in the CPK, which is the creatine phosphokinase, and the weight and the age issues, and we saw some other data sets as well, where you can use your own data to explore three variables, one of them being outcome variable, the other being explanatory variable, and how you can use them. This is good work. But as you know, with the bivariate case, as is with the multivariate case, there are always some data points that will not exactly conform to the theoretical, nicely cleaned data that we are habitually, that you may expect in a textbook case. So there will be data sets that are influencers, there will be data sets that are outliers, there will be data sets that are very different. So what do we do about these things? And this is the objective of this bit, the more advanced topics on doing the multivariate data analysis or multiple linear regression. Again, we are going to be confined to one continuous variable, and both variables that are in your predictors are going to be continuous variables. So we'll take a look at this. We'll start talking about multicollinearity problem, which is like what happens when both the variables are kind of related one with the other. What do we do these things, right? So again, bring out your RStudio, let's load up your data, and let's get working. Thanks.
Now we're going to talk about the second part of multiple linear regression. In the previous iteration of the multiple linear regression, you learned certain things that we kind of extended over the bilateral linear regression. We said that it was an extension of the two variable case, and we showed that you can do certain things. For example, we showed you how interaction terms could interact with your individual variables. We showed that how intercept terms could, or the regression coefficient of the intercept term could interact with the intercept with the beta coefficients of each of these variables, and how that would then change if you took out the intercept terms and interfere with the variation of the beta coefficients, etc. We also showed the basic theory and the kind of layout of the multivariate linear regression. We learned a little bit about the diagnostic plots and interpretation of the diagnostic plots. In other words, we would first start with a graphical exploration of the various variables, which is why we would run pairs plot. And that pairs plot would be very useful for us in giving us a sense of how we could view the different different relationships among the different variables. And in all these cases, of course, the outcome variable is a continuous variable, and the explanatory variables are also continuous. So we saw some of these things. Next, when we start talking about the multivariate linear regression, we need to look a little bit more in advance, because we saw that although we assume that the outcome variable as well as the explanatory variables would obey the several assumptions, it is quite possible in many circumstances that that assumption is violated. Not only this, when we examine the various plots, it may be quite obvious that a linear relationship is probably untenable. So what would we do? How would we examine if that, how would we examine that in using R if we see that a linear relationship or a linear extrapolation is probably not the best way to describe the association between the various variables? Tricky problems. But it turns out that R is more than equipped to give you that understanding. So if you want to transform some variables, you could do that. if you would like to then examine the transform variables, you could do that very, very easily. And you could run quite a bit of diagnostic plots and other things that are very, very useful. Once again, while we are going to explore many of these issues in this particular framework, the focus here is on how to get those work done by R, not necessarily, or how to get those work done with R, not necessarily the nitty-gritty of the theoretical principles that underlie such operations, because these are far more complex, and not everyone can be covered in the course of this lecture. It is beyond the scope of these presentations, but having known those things, there are certain things that you can do using R as your guide, which is where the value of this comes into the picture. I am Arindam Basu. I'm at the University of Canterbury at Christchurch in New Zealand, and this is part of the ePathshala program. As with in general, to remind you with the motive of this, we start with some introduction of some of the basic principles, and we then describe some of those principles as far as we can, but we cannot do too detailed an attempt at this. We run some demonstrations, and then we summarize in the end what we're doing. The objective of this particular deck of slides is to introduce you to the concepts of kind of fitting multiple linear regression models, because it is very important when we run multiple linear regression models, in fact any linear regression model for that purpose, we should have a good idea that this model fits. There is this saying which has been attributed to, I think, that there should be a corresponding fitting of the data and the model. So the model should fit the data that on the basis of which you have devised the model, and the data must also reciprocally or correspondingly go back and fit the model. So this mutual fitting of the data and model are very, very important. If that doesn't happen, then you know that something is amiss. So one of the core competencies in running any statistical software which runs multiple regression models and multivariate models is to make sure that the models fit, and using the parameters and be able to extract those parameters or extract those concepts to know that the models are going to fit one with the other. So that's the most important principle that we're going to learn here using R. The second thing, which is very important, is that if you run multiple regression models, which means that because you are doing multivariate regression, so which means that you're not just confined to one outcome variable and one explanatory variable, you're actually using an explanatory variable and several other covariates. So there will be more than two explanatory variables here, or at least two explanatory variables. When there are two explanatory variables and there is one explanatory variable out of conceptually relevant, then it is not very difficult to see that which variable is going to fit better, although it's very quite contentional. But the problems are simpler. But it becomes a problem of permutation and sort of a combinatorics when you're dealing with more than three or at least more than three explanatory variables. One of them may be the main explanatory variable. The other two may be the covariates that should go into the model. How will you know which model is the better of the three, the best of the three, and the better of the remaining two? Is there something that we can do? The other side of the problem is this, that if you have got multiple variables, the challenge then becomes as to which variable should go first, followed by which variable, followed by what variable. So the order of the selection of the variables become very, very important. So there are three problems that need to be paid attention to. One is that how do we know that the regression model fits best? What is the way in which we can find it out? How do we compare? And the third thing is, what would guide us as the sequence of the variables that should go into the models? Let's examine some of the preliminary ideas before we move on to this. One of the first things that we have been emphasizing in this series right from the beginning is be open to the idea of graphically examining the variables before you do anything. In other words, before you launch into complicated model building, be open to the idea that you can graphically examine these variables, which is very, very important. Because graphical examination will give you not only a hint, but will give you a lot of information as to whether a linear model at all is useful. It will also help you to figure out when and whether and how you're going to look for outliers and influential points for each corresponding pairs of variables. So a careful graphical examination of the explanatory variables themselves is important. And it is not just an examination of the outcome variable with the explanatory variables, but the mutual relationships amongst the explanatory variables is also very important. One of the reasons why this is important is we have kind of seen that in the previous simplistic example of a multivariate linear model. When we took out the interaction term, we saw that because the interaction term was correlated with one of the explanatory variables, therefore that impacted the regression estimate. A corresponding effect happens when more than one explanatory variables themselves are related one with the other. This is the problem of collinearity. We will learn a little bit more on collinearity in our in due course of this lecture. But that's an important thing. And therefore, it is very important that you should construct a pairwise matrix and take a look at the pairwise matrix first. Then what you need to do is you need to take a look at to fit the multiple regression equation first. This is tricky because sometimes you need to fit all the variables together, or you can fit all the variables together and then gradually take out one after the other variables to see how the multiple linear regression works. Or you may have to fit the most important variable first and then subsequent variables get added. So there are all styles, the different styles in which you can build a model. And then once you have started building those models up, you will need to figure out the outliers and the influencers that are present in the explanatory variables. So you may need to take out the outliers and influencers and refit the model to examine that model over again. And one of the ways in which you can make a real impact is if you start looking at the plot of residuals versus fitted values. And this is important because the multivariate assumptions, that is, the residuals are kind of do not vary with the fitted values. In other words, the residuals do not show any association themselves, or the residuals do not show an association with the fitted values. Is a very, very important assumption. And if you find that there is an association between the fitted values and the residuals, then that tells you that the model is not likely to be a good model for a linear model. So that's the reason why you need to plot the residuals with the fitted values. It's not so much of a problem if you fit the residuals with the explanatory variables, because that may or may not matter much. So always fit the residuals against the fitted values and examine them. So these are some of the preliminary ideas that I wanted to swing by. So let's take a look at the data set that we're going to use for this particular set of examples, or running with this notion. As with the other things, as I keep on iterating it and over again, use your own data to run through these examples. You do not do not have to necessarily use the data that we are using. However, for the sake of demonstration, I'm going to use the library DAAG, and you have met this library before. This library is known as Data Analysis and Graphics by Professor John Maindonald. Professor Maindonald is a professor of statistics at Australia's National University, and it's a very, very useful package, and there's a very nice textbook on learning R, particularly with the data analysis and graphics. I have included a PDF copy of the data analysis and graphics book on with the resources files, which is available off the CRAN resources. You should download and read the whole PDF and work with the exercises. It'll give you a lot of information. So in that library of data analysis and graphics, they had modified a very well-established data set which was put out by Brian Ripley and his colleagues, called Scottish Hill Races, and they call it Data Hills, where the investigators were interested to find out that, what are the different record times and distances and the height climbed by people who participated in Scottish Hill Races in the year 1984. So, but what they had done basically is that they had transformed some time intervals, etc., from the original Scottish Hill Races and created a data set which is known as Hills. And we're going to use this data set for this particular analysis. And in that data Hills, you have the time is noted in hours as opposed to minutes. And then you've got the distance and the height climbed for the Scottish Hill Races. So the first, of course, is that we start with a scatterplot matrix of the various variables, and we start with a summary of the hills. Now this is something very interesting. If you take a look at these things like summary, pairs, and library, let me go over this code. The summary tells you that we are going to summarize the variables of the hills data set. The pairs hills tells you that you can create a scatterplot matrix of the different variables in the hills. So as simple as that. It's very, very simple. You can see that one of the most important issues with R is this, that the codes are really simple. So if you want to have a scatterplot matrix, all you have to do is just pairs and hills. That's it. It just does it for you. Of course, you can spruce it up with the title, the x-axis labeling, the y-axis labeling, everything that you want to do with this. But the bare minimum is just put a plotting command of pairs. Done. The other thing that you can do is use another function called SPLOM, SPLOM, and for that you have to use the famous lattice library. Now, I just wanted to keep things really, really simple, so I didn't really ask you to do this. But you can do alternatively use library lattice and use the SPLOM function. When you do that, this is what you get to see. You get to see that there is a minimum, the 5-number summary for the distance, climb, and the time. Note that all the 3 variables are continuous variables. And you can see that there is some sort of a relationship between distance and time, and time and distance. Time and distance could be linear, but you know what? There can be an issue with time and distance. So time increases as distance increases. But what is the relationship between distance and climb? So, as the climb inclination increases and the distance increases, time will increase, but probably not linearly. So that's another issue that we need to explore this. And also, if you were to go back and forth with these data sets, you'll see that the range of time is rather large. You can see that it's quite a large range. And also graphically, you can see that the times are kind of bunched up in the lower ends. So a lot of people finished faster. Some people would take a long time. So bunched up with a long tail. And conceptually, we could argue that time cannot be a linear relationship of the distance, because as the distance goes up, time also goes up. But it is human beings after all. Therefore, time will prolong more for longer distances than for shorter distances, which tells you that if you factor in the distance and climb, you can almost have a power relationship. So time to the power of, say, b1 times, or the distance to the power of b1, which is the coefficient, times the climb, right? That is also raised to a certain power of b2. And when something like that happens, from our math, we know that we can take a log function. So log time is equal to log a plus b1 times log distance plus b2 times log climb. This is the conceptual model we can jolly well test in a multilinear regression model. This is something very important. That is, when you set up a model in a multiple linear regression framework, you fit the model not just on the basis of statistics, but you fit the model on the basis of your concept of life, the theme, the theory. That will override everything, the underlying truth that you want to capture. So we could run this model, or we could run these graphical explorations as it is, but let's see if we could take logarithms and then run the pairs, what happens. Once again, explanation of the code. You can see that we just run the pair of the log of the hills, sufficient to run everything. And then because it is a kind of new function, let's say hills 0.log lm, and then we run the linear model with the log time against the log distance plus log climb. Okay, keep matters really simple. And then you have made these friends before. We set the parameters, and we say that we're going to put it into a 2x2 matrix to see what happens. And then we reset it to come back to 1x1 larger matrix, of course. So we see what happens. When we did this, compared with the previous ones, you can see that this particular scatterplot matrix with transformation looks a little bit more consistent. So our initial idea of distance times climb as power functions that could explain time kind of makes sense. And the distance and climb are now more linear than before. Okay? But here is the thing. We can see, if we look carefully, then there is one outlier that needs to be taken care of. So we know by this time that in order to find out an outlier, we need to run some diagnostic plots. So diagnostic plots are hereafter. When you look at the diagnostic plots, you can see that the Nock Hill race, observation number 18, is an influencer because the Cook's distance exceeds the magic value of 1. Interestingly, it turned out that it had a race time of 1.3 hours for a 3-mile stretch. Obviously, there could be some mistakes. So this was then, in the original data set, was reset to 0.3 hours rather than 1.3 hours, which was their actual time. And then the plots were rerun after removing observation 18. And once again, if we do this, we see that things have improved slightly, although you could still argue it is, whether it's a fully linear model or not, it's kind of open to question. So here is the thing, that we have been talking about adding an interaction term. That we say that, look, if we multiply them, then there is one way of doing it. But it is also possible to add them in different other ways. And that is, we could actually mix them together, which means that, yes, using the log transformations, we can add them up. But adding the log transformation only adds them up in terms of the power that was present. It doesn't really add up the interaction term between hill and climb. So not between the distance and the climb. So we need sort of an interaction term to build into this. So let's take a look at how do we include interaction terms in a linear model. I have presented here somewhat of a complicated interpretation of this, but what you could do is just simply put in a multiplied term, and it would still do the same thing. But here's what I have done mainly for your learning, is we have set it up in a way that the hills to log lm becomes an object which will receive the product term of the distance times climb. So log distance plus log climb plus log distance. Then we have put together a colon and then log climb. This is the crucial bit. You can do this yourself, or you can just simply type log distance times log climb, and the software will do that for yourself. So then we can have two other functions that are very important. First function, and I'll go over this, is first one is an ANOVA of this multiple linear regression model, and the other is checking the various steps through which the model is going to learn. And that is done by using the function called step. So I've saved it into an object called step check. I'm first going to learn and explain the interpretation of the ANOVA table. ANOVA stands for the analysis of variance components. Now, because we included a interaction term, the first thing that it did was it kind of put the log dist and log climb as a linear model. It did not put in the log distance times log climb in the first place. So that was the first thing that we wanted to do, and then interpret them, and then check that with the interaction term, right? So what it does is this, that it gives you a sense of the residual sum of squares, and then you can see that the sum of squares for both the models, and on the basis of this it's going to compare the second model with the first to say, okay, if addition of the interaction term, did it change the model sufficiently to make an impact? And that is something that you find out from the F statistics and the probability of that F statistics, the p-value for the larger model. And here you can see that addition of distance times climbing did not make much of a difference in this particular model. So for the sake of parsimony, you could remove the distance time climb, that component, from the model and just run an additive model as such, and that would be just as fine. So that's one way of looking at it. The second thing that you can do in order to get a sense of whether the performance of that model is better or less is to use what is known as an Akai-Key information criterion. And let me explain that a little bit in the context of what we're discussing. Now, we are familiar with the adjusted R-square, which tells us a little bit about the explainability of a particular model that you put into it. So in other words, how well or to what extent does the addition of the explanatory variables explain their variability in the outcome variable. So the adjusted R-square, after adjusting for the degrees of freedom, will give you that information. If that is very high, it's very good. Then you know that the combination of these terms were kind of appropriate because they were explaining this. But it still does not tell you whether this combination of the predictor variables are going to be good predictors of the outcome variable or not. This is a problem. Because on the one hand, it can kind of explain the variation in the outcome variable. That's good. But if we put these different variables together, what is the extent to which it can predict the outcome variable? And is one set of mix of explanatory variables better than another mix of the explanatory variables, even though they can explain X percentage in the outcome variable? That question is addressed by this criterion, which is known as Akaike information criterion. So what Akaike information criterion does is kind of a log likelihood to the extent to which that prediction can be given. So think of it like this. And here is the deal. Like, the lower the value is, that is in terms of say minus 121, is probably probably a better value than minus 122. So think about it. Minus 122 is actually lower than minus 121 in terms of the Akaike information criterion. So if you add the distance times log climb, you're not actually gaining much, you see. Because if you start with the highest possible value and then you stepwise see to the extent to which it is reducing your value. So you start with minus 122. Okay, so 122 is your starting point. And then what you do is this, that you will then put the next bit where you're going to put the term of the interaction term, and now we see that it's moved up to 121 minus 121.78. So then you see that it's better to stick with the additive term rather than the multiplicative effect that you get to see. Okay. So in that sense, Akaike information criteria is an information measure whether to say that there is this whether you get a better predictive power. So the model that gives you the smallest Akaike information criteria is preferred. So in this particular case, just the additive model should be a better model. Okay. But what is really, really important is this, that not the absolute Akaike information criterion, but the changes in the Akaike information criterion is what we are going to look at. So in order to summarize everything, we say that the R-square and adjusted R-square are useful, and adjusted R-square should be preferred over the raw R-square. Akaike information criterion is a performance measure of the model. Model with the best predictive power has the lowest Akaike information criteria. But what is more important is this, that the changes in the Akaike information criterion is more important than raw value of the Akaike information criterion. In the next, we're going to talk about a couple of other things. One is, how do we select explanatory variables? And to be absolutely honest, the most important thing that you need to do is that whether it makes sense from a theoretical perspective. That should kind of be very, very important. So which variables to include? Well, which variables explain best? There are some indications about substantive importance of these variables themselves versus whether we can bunch up any number of variables and that's going to explain the variability. Now, that's not very, very good. And there are some other conventions. These are more like rules of thumb rather than anything else. So don't take them too seriously. It's just that the number of observations is like 10 times the number of variables. And if you are dealing with a qualitative variable, as a categorical variable, then depends on the number of the categories you have. So the number of categories minus 1, then multiplied with 10 will give you that. So if you have got a categorical variable with 5 categories, that's equivalent of 4 quantitative variables, then times 10. Okay, and as I say, fit the most important variables based on your knowledge. Now, the other thing that is very, very important is this, that some variables are linear combinations of the other variables, and that's something we'll take a look at when we start talking in terms of the what do we in ANOVA. It becomes very, very important. So there is this thing called LIS, and then you run the model, and that'll give you if there is collinearity problem amongst the variables that you introduced into the model, and it'll give you what kind of transformations to make. And you can take and you can conduct a test in order to test for multicollinearity, which means that if a number of explanatory variables are given. These variables themselves can be correlated with each other. That introduces a problem called multicollinearity, and you can use a variance inflation factor function to test the extent to which their variance get inflated, as we had seen in the previous example. So to summarize, we discussed issues around multiple linear regression. We ran some of the things. We learned how to assess the model performance using Akai key information criterion, and we touched on the basis of the variable selections and multicollinearity. So we will, in our next study, we'll take a look at what is known as analysis of covariance when we have got multiple categorical variables in questions. So thank you for paying attention to this.
Welcome back. This particular session, that is at the end of this bit, we have understood that we could talk about the multivariate cases with 3 variables. And at the end of finishing or completing the multivariate part 1 and part 2, you should be more or less confident about using R for exploring the associations between a range of variables. And those range of variables, basically, by that I mean that the outcome is a continuous variable. The explanatory variables, all of them are continuous variables. Now this is fine because, you know, if you know how to use 2 variables at a time and then more than 2 variables at a time, this is very, very useful and powerful ways of exploring the associations of different variables. But there is a catch. So far, you have learned only to deal with continuous variables. But what happens if you face with a variable which is, one of the predictors is continuous, the other is a continuous variables? So what do you do about them? This is going to be the object of the next bit, in which we're going to look at analysis of covariance. So on that note, I sign off now.